So I did a mistake last time when I explained Woodline mirror descent for adversarial bandit case. So at that time, I didn't mention the range of reward. Essentially, all the theorem what I explained before hold only when the reward is negative. Okay, so every reward is negative, then all the theorems hold. But the reward becomes positive, there is little uncomfortable things, and the theorems becomes not correct. Okay, I explain why such bad behavior happen and why the negative reward is not strong assumption, and how to resolve the negative reward constraint. Okay. Right. In the previous time, I explained the Forel algorithm can be applied to bandit problem, and the Forel algorithm can achieve very nice result. And EXP3 is one special case of Forel approach for the adversarial bandit case. We basically optimize this online convex optimization problem, basically solved using this pi convex regularization. And every time, instead of just simply reward vector, because we don't know the other reward value except the played arm, we normalize, we remake x bar vector using important sampling so that expectation x bar is equal to xi, is equal to x original x vector. That is important sampling technique. And for the adversarial bandit case, one common class of the cost function regularizer is pi beta function defined as follows. And exp3 is extreme case when beta equal to 1. So when we define the update rule using this pi regularizer function, we have this rule. Okay, here lambda is just a constant that make pkt plus 1 becomes probability vector, which means the element of pkt, all non-negative and sum of element of pkt equal to 1 all the time, right? But here, what is the problem is when the reward is negative, this is fine. This is absolutely fine. Okay, so this negative reward only increase this value. So always this value keep the positive value. So it is clearly defined. We can clearly define the p prime k t plus 1 from this equation. But the problem is when xkt is positive, okay, then there is issue. Why? There is some chance this value subtraction can make this value negative. When this value is negative, p prime k t plus 1 or minus beta, that is a little bit weird, right? It is p prime kt plus 1 is not well defined some cases. Okay, but it is still okay. Why? Because when we know the max of when we know max of reward, we can subtract this max of reward all the time. This is totally fair because we subtract same constant every time slot. Still, we are finding the same best sum. We just implicitly subtract same constant all the time and learning the algorithm. Then this optimization problem just simply this one minus just some constant, same constant all the time. That's it. So there is no issue. Okay, so we can convert the original problem to negative reward case, and we can keep the same algorithm. No issue. Okay. So when we have the reward range from 0 to 1, just subtract 1 all the time. That's fine. That's absolutely fine, and we still can find the best quickly, and we can still say square root t regret, square root t capital K regret. Okay. So when we subtract same constant all the time, we do not change the problem, so problem solved. Okay, there is no issue. Right. Otherwise, if you want to keep the same regret, if you don't want to subtract the max of reward all the time, okay, still there is a possible way to do this simple update rule using a very interesting trick. So let's say our reward in between 0 and 1. So let's say x vector always 0 and 1 vector. Okay, every value, reward value in between 0 and 1. And here we introduce p bar such that p bar t is equal to 1 minus gamma pkt plus gamma times 1 over k, like a exp3, original exp3 algorithm. Okay. Then, and here gamma is equal to 2 times capital K, 2 minus beta over beta times eta. Okay. So this. Okay, and then the Adversarial Bandit algorithm play with p bar instead of p, and defines x bar with p bar accordingly. Okay, which means we keep the pt value all the time. That is the same. We keep the pt value. We update p prime t plus 1 from pt. Okay, everything the same. Only different thing is, although we have pt value, play with p bar t. Okay, just simulate our algorithm performance using p bar, not the original pt value. So why this is useful? So from online mirror descent algorithm, we know this optimization performance result. So to analyze the regret, we just need to the radius of your input domain with respect to the Bregman divergence, and we need to analyze the variance with respect to the same Bregman divergence. So here we follow the same rule, same logic, except this part. In this part, before we use Taylor expansion using 1 plus x to the alpha, and when we have alpha negative and when we have positive x, then using Taylor expansion we can well upper bound this value. But here, because we have a negative x value, and the negative x value cannot be well upper bounded by simple Taylor expansion, especially when x close to minus 1. To use the same technique, we have to limit the x range. We have to limit x close to 0. Okay, x not too deviate, so x cannot be close to minus 1. Otherwise, the upper bound to use Taylor expansion is not good approach, I believe. And that's why we have to introduce gamma, additional gamma exploration. The additional gamma exploration and new definition x bar restrict the range of x bar. So here x bar is kind of important sampling reward vector. So when the minimum probability is very tiny, the x bar value can be very huge, and the very huge x bar value can make this value close to minus 1. So this value close to 0, or even this can make this value can be negative. This is not good. Okay, that destroys every analysis. So we restrict the x bar value using additional gamma term, and using the additional gamma term, we can limit the range of x like this. And using this limited range, again using Taylor expansion, we can upper bound this polynomial. And using this upper bound, we achieve almost the same result. And using this almost the same result, we have this almost the same regret bound, except this, we have additional gamma t term. This is because we use additional gamma exploration term. With probability gamma, we purely explore all the arms with this uniform distribution. So we can roughly upper bound the regret at each time slot using gamma, the additional regret. Okay, so gamma capital T is additional regret due to the gamma term. Okay, so using the same technique in original EXP3 algorithm, we can achieve the still powerful regret result. But without this technique, we essentially can achieve very nice regret bound using simple trick, subtracting the max reward all the time. Subtracting max reward all the time make all the rewards to be negative, and the negative reward can utilize previous very well constructed technique that make very nice result. Okay, so when you design an algorithm, I recommend to use some simple technique, simple trick, minus subtract the max of regret. That is simple and very useful for this analysis. But if you don't want such subtraction trick, okay, then you have to introduce additional gamma to restrict the range of x bar, and the restricted range of x bar still make a good regret.